Okay, welcome to the first lecture of week 9. And so far in this analysis part, we have covered chapters 1 and 2. Chapter 1 was on real numbers and the least upper bound property of the real numbers in particular. And then chapter 2, which we have just finished, was on sequences and their convergence. And today we'll begin with chapter 3, which is on continuity. And the rest of this term, we will discuss this chapter. So the next 2 weeks basically. So we are going to discuss continuous functions and their properties. Okay. So the setting is that you have a function which is real valued and is defined on a set which we assume to be an interval. So recall that intervals were these connected segments on the real line, and our function will be a real valued function defined on such an interval. So among all the functions which you can think of, which are real valued living on an interval, there is a subclass of functions which are continuous on this interval. Okay, so continuous at each and every point of this interval. So we'll explain what's meant by this concept of continuity of a function on an interval and the continuity of a function at a point of the interval. And the reason we are learning about this special class of functions is because continuous functions have nice properties. For example, today we'll learn that continuous functions preserve convergence in the following sense. That whenever you have a sequence which converges to some point in that interval, and you look at the new sequence, which is f of xn, where xn are the terms of the old sequence, then that new sequence is also convergent, and in fact the limit of this new sequence is f of the old limit. Okay, so whenever you have a convergent sequence in the domain and you act f on it, then that new sequence that you get in the codomain, that's also convergent. So in that sense, the function preserves convergent sequences. Next time we'll also see that composition and restriction of continuous functions is continuous. So, with respect to these operations, you don't leave the class of continuous functions. And finally, in week 10, we will learn about these two very important properties which are possessed by continuous functions living on special types of intervals, namely compact intervals. Okay, so over here, most of the time we'll just work with general intervals, but these two theorems work on this special type of intervals, which are compact intervals, namely these are bounded and the endpoints are included. Okay, so for that, then you have these two things, namely the intermediate value theorem and the extreme value theorem. The intermediate value theorem, roughly speaking, says that f assumes all the values between fa and fb. So if I have a y, a real number which lies in between these two values, then there is some x in AB such that f of x is exactly this y. Okay, so all the intermediate values between f of a and f of b are assumed. And so that's the intermediate value theorem. Of course, we'll state it precisely later on. And the extreme value theorem says that if you look at the image of this domain, so you look at this set f of AB, then that set is bounded. So it has an upper bound and a lower bound, and since it's non-empty, it also has a least upper bound, the supremum, and the greatest lower bound, the infimum. And in fact, these again belong to the set. Okay, so there exist some points C and D in this interval, such that f of C is equal to this supremum and f of D is equal to this infimum. Okay, so that's roughly so it's sort of the extreme values are the supremum and infimum, and they are in fact attained. That also we'll learn later on in great detail, but I'm just trying to give you an overview. So the aim of this chapter is to understand what continuous functions are, and moreover to look at some of their properties. For example, they preserve convergence, they are closed under this composition, and they have this intermediate and extreme value theorems as properties. Okay, so let's begin with defining what's meant by a continuous function. Now, in everyday language, we use the word continuous. For example, you might say that, well, it was a continuous process. What you mean is really that there were no breaks or interruptions or sudden changes in that process. In the same way, we can think that a function is continuous if there are no jumps or breaks sort of in the graph of the function. So the graph of the function is the collection of all points x comma f of x. Okay, so this ordered pair x comma f of x, the set that you obtain, is thought of as the graph. And when we say that a function is continuous, we mean that its graph has sort of no jumps or breaks. Now in everyday language, when we think that some process has a break, that break appears at some point. In the same way, when we say that the function has no jumps or breaks, we first envisage that if at all there's a break, it occurs at some point. So we'll first define what it means for a function to be continuous at a point. So that would mean that there's no break at that point. And if there is no break at any point, in other words, if the function is continuous at each and every point, then we say that the function is continuous on the whole interval. Okay. So before we define what's meant by a function being continuous on the whole interval, we'll first explain what's meant by a function being continuous at a point. Okay. Now, intuitively, we would say, for example, a function which looks like this. You see, for values less than c, it's nice like this. But at c, it suddenly takes this value. So this is what f of c is. So that's indicated by a solid point over here. And there's a hole over here, which means that, okay, the values of f at x's which are close to c but less than that are somewhere over here. But at c, it jumps to this value, and then it continues with values which are close to this f of c. Okay. So we would say that this function is not continuous at c, because obviously there's a jump at c. So what we actually want is that f of x should stay close to f of c whenever x is close to c. And you see that's not happening over here, because this is the value f of c. And when I'm close to c, okay, if I'm close to c but above c, then you see that as I approach c, indeed the values are staying close to f of c. If x is less than c but is approaching there, you see the values are far away from f of c. The values are over here, and there's this big gap between the what f of c is and what f of x is when x is very, very close to c. It doesn't matter. No matter how close I get to c, the values stay far away from c. Okay? So we claim that this is what is capturing continuity. What we want is f of x should be close to f of c whenever x is close to c. So somehow we have to translate this into some precise mathematical statement, and that should mean that f is continuous at c. And clearly then this is not continuous at c, because no matter how close I get to c from below, I stay far away from f of c. So it's not the case that whenever x is close to c, f of x is close to f of c. Okay, so this would be not continuous at c. Anyway, what we'll first do is give a formal mathematical definition, and then we will consider sort of contrast two examples pictorially. One of a function which is continuous at c, and one which is a function of this type which has a break, and we'll see that our definition does capture this notion that a function is continuous if f of x stays close to f of c whenever x is close to c. Okay, so here is the formal definition. Okay, so the setting is that you have an interval and you have a function which is a real valued function defined on this interval, and there's a point c belonging to this interval, and we are discussing the continuity of the function at this point c. So here is the definition. We say that the function is continuous at c if given any distance level epsilon positive, there exists a distance delta positive, such that whenever x is in the interval and satisfies that its distance to c is less than delta, we are guaranteed that the distance of f of x to f of c is less than epsilon. Okay, so once again, let's first read it mathematically. F is continuous at c if for every epsilon positive, there exists a positive delta such that whenever x has its distance to c less than delta, so mod x minus c is less than delta, we have that mod of f of x minus f of c is less than epsilon. Okay, so now intuitively what does it mean? So given any distance level epsilon, so what I have is here is c and here is f of c. Now I am being challenged that f of x stays close to f of c within the distance of epsilon. So what does that mean? That means that if I look at f of c and I add to it epsilon, okay, so on the vertical line f of c plus epsilon is somewhere over here, and all of these points, okay, on the vertical line have their distance to f of c less than epsilon. Okay, similarly I can take f of c and go down through a vertical distance of epsilon, and all of these points on the vertical line, yeah, have their distance to f of c which is smaller than epsilon. So this vertical line segment is exactly all the real numbers y whose distance to f of c is less than epsilon. So when I'm saying that given any distance epsilon positive I want this, what it means is that the corresponding f of x lies below this line and above this line. Okay, so it lies between these two horizontal lines. Okay, and the function is said to be continuous if no matter what such width of epsilon you give me, okay, about the horizontal line f of c, so no matter how small such a strip you tell me, there should exist a delta positive such that whenever I take x's within a distance of delta from c, so what's that set? Well, that's this interval centered at c with distance to c as at most delta, right? So it is this open interval c minus delta to c plus delta. Whenever my x is over here, this is saying that whenever my x lies in this segment, the corresponding f of x, okay, satisfies this. So it is below that top horizontal line fc plus epsilon and above this bottom horizontal line f of c minus epsilon. So the graph of the function, all the corresponding f of x's lie in this strip. Okay, so whenever I look at this rectangle which is produced by looking at these two vertical lines which are produced by displacing c to the right through a distance of delta and left through a distance of delta, so whenever I take my x's in here, the corresponding f of x lies below this and above this. Okay, so the graph of the function then lies in this shaded rectangle. Okay, and this should happen with every epsilon positive you specify to me. So no matter how small the width I specify, presumably I have to take a smaller delta so that I'm assured that then the graph lies below this smaller, in this smaller width around f of c. Okay, so right now the definition is still a mouthful, but we'll soon see examples of this and we will get more and more familiar with it. But the first task is to see that this does capture our intuitive feeling that f is deemed to be continuous at c whenever f of x stays close to f of c, provided that x is close to c. Okay, so we'll see that in a minute, but let me continue with this one more definition, namely that the function is said to be continuous on the whole interval if it's continuous at each and every point. So there is no break at any point. No break means that it is continuous at every point, and so we define that the function is continuous on the whole interval if for every point c in I, f is continuous at c. Okay, and sometimes we drop saying on I, then it's understood that it's continuous on the domain. Okay, so the function is said to be continuous if for every point in its domain, which is this interval I, the function is continuous at c. Alright, so we have seen this definition of continuity at a point, and let us make sure that we understand what it means pictorially once again. And what we have drawn over here are two instances. One where your interval is like this, okay, and the function is nice and continuous at this point c in the interval. You see, there are no breaks. I can draw the graph of this function sort of without lifting my pencil. On the other hand, I have drawn the graph of another function where clearly there is a jump. You see, you have this thing over here, it is nice and continuous up till here, but at c it does not take the value which is the value at this hole, but rather it jumps and assumes this solid point as a so f of c is this height as the number, and then it continues nicely and smoothly. Okay, so over here we would expect the function to be continuous, and over here we would expect the function to be not continuous at c. Here the function is continuous at c, here the function is not continuous at c. So let's revisit our definition and see if it sort of intuitively captures our feeling that this function is continuous at C and this is not continuous at not continuous at C. Since over here the function is continuous, okay, given any epsilon positive, so this is the height f of C, and I lift it up through a distance of epsilon and lift it below through a distance of epsilon. Then on this vertical line segment, the points over here have their distance, okay, the heights over here have their distance to f of C as exactly less than epsilon. Okay, so all the points over here. Okay, so what do I have to then do? Then I have to produce a positive delta such that whenever I am within a distance of delta from C, I am guaranteed that the corresponding f of x lies below this line and above this line. Now over here, what should the delta be? You see, if I take too large a delta, for example, if my delta distance is so much, okay, like this, then I will have my f of x which goes outside this strip, you see, it goes outside this strip, it's over here. So I should choose a more conservative delta. I should not choose such a big delta, but I should reduce it so that then the graph lies below this and above this, right? So it seems that some delta like this would work, right? Because that's where it hits this line. So some distance delta like this would work on this side, okay? But if I go the same distance, oh, perhaps maybe that's not so good. So over here, I seem to be needing a smaller delta, okay? So if I choose some conservative delta like over here, right, and then I look at these two vertical lines, okay, and then we visibly see that whenever my x is over here, the graph is indeed lying below this top line and above this bottom line. So this is a good delta. So for this epsilon, it seems that a delta as shown in this picture does work. Okay, and it has to work because, you know, we intuitively expect this function to be continuous. There are no breaks. Okay, with this epsilon it works, but it should work with every positive epsilon. Okay, so what happens if I had a smaller epsilon? Yeah, indeed. Then also, you know, if the horizontal line were here instead, something like this, then indeed I would have to choose a much smaller delta so that again the graph would lie below this line and above this line. Okay, so our definition does seem to make this function be continuous at C. Okay, that's good news. And our definition should also prevent this function from being continuous at C, because we see that there is a break here, right? So this function better not be continuous at C. There is this big gap. So if I choose my epsilon to be such that, you know, it is something smaller than this, than the height of this jump, okay, so something like this, okay, or I take the epsilon so that it is smaller than this height, so some epsilon like this. Okay, so this is what f of C is. I lift it up through a distance epsilon and lift it below by a distance of epsilon, and this epsilon is chosen smaller than this jump. Then what happens? Well, no matter what positive delta I choose, okay, we will see that although from over here, for all my x's over here, the corresponding f of x does lie below this line and above this line, okay. However, when I approach C from here, then although this is satisfying that its distance is smaller than delta, you have that the corresponding f of x, this red portion, is not lying in this strip. You see, it is outside this strip. And so this function is not continuous at C. And this will happen with, you might say that, okay, the delta you chose was too large. What happens if I choose a smaller delta? Suppose I choose a very tiny delta, something like this, a very tiny width here. Then still you will have this red portion, okay, but of course a smaller red portion, but there will be points which do not lie over here. And so we see that this function is not continuous at C. Okay, so this was of course some hand-waving intuitive arguments, but it is good to have seen this because we do see that our definition seems to make functions of this type continuous at C, and functions which have an obvious jump, we do see that it is not continuous, right? But now we will actually see some examples and get more familiar with this notion. Okay, so let's start with some simple examples, because then the computation is not so difficult and we will get more and more used to this definition. Also, we will soon learn some theorems which allow you to deduce the continuity without having to go through the definition. A bit like what we did with sequences. We found that there are ways of deducing that the sequence is convergent and finding out its limit without actually going through the definition. Okay, in the same way we'll learn some theorems of that type over here also. So that's why I have chosen some simple examples so that then at least the definition becomes very clear to us. So here is the first example. I consider the constant function, the function which is defined where the interval is the whole real line and it is just the constant function, say with constant value 1. So the function has graph which looks like this. It is just this horizontal line. Okay. My claim is that the function is continuous at each real number. So let C be a real number and I want to show that the function is continuous. What does it mean? It means that given any epsilon positive, I have to produce a delta positive. So that's the question. What should the delta be? So that whenever x is a real number whose distance to c is less than delta, I am guaranteed that f of x minus f of c, its absolute value, is less than epsilon. So in other words, the distance of f of x to f of c is smaller than epsilon. So an epsilon has been given and I want to produce a delta. But what is this f of x? Well, f of anything is equal to 1. And what's this f of c? Well, that's 1 as well. So this is just mod of 1 minus 1, which is mod of 0, which is equal to 0. And epsilon is positive, so of course this is always true. So it seems that it doesn't matter what delta I choose, because no matter what delta I take, this thing is always true. So, well, I just wanted a delta positive, so any positive delta will do. You take your favorite positive number. Okay. So this was just the rough work, but now let's write it down properly. Typical with analysis that we first do some rough work, we make a plan of the proof and then we write it properly. Okay, so let epsilon be positive and we can take any positive delta. For example, 1 is a nice positive number, why not take 1? Okay, so delta equal to 1. In fact, any positive delta would do. And then if you have any x in the interval, so the interval was the set of all real numbers here. Yeah. So for any x in R which satisfies that its distance to C is less than delta, which we have chosen to be 1, why not? We have that mod of f of x minus f of c, the distance of f of x to f of c, is equal to mod of, well, f of x is 1, f of c is 1, so this is just mod 0, which is 0, and indeed epsilon was positive, which we were given, so this is of course true, always. And so, given any epsilon positive, I have produced a delta, namely this delta equal to 1, such that whenever x satisfies this, its distance to c is less than delta, I have that the distance of f of x to f of c is less than epsilon. So I have checked the statement in the definition of continuity. Okay, so f is continuous at c. So what actually happened? What did we do? Well, this is what happened. This is, we took any real number c and we were showing continuity at that point. F of c is equal to 1. Okay, when I was given a positive epsilon, I have lifted this 1 through a distance of epsilon and also below. So all the points all on this vertical line segment have the distance to 1 as less than epsilon. I wanted to produce a delta such that whenever x is within a distance of delta from c, I have that the corresponding f of x lies below this and above this. But the value does not change at all. It's always equal to 1. So it's always equal to f of c. So, you know, I could have chosen any delta I wanted. I chose delta equal to 1. I could have delta equal to 80,000 if I wanted. It doesn't matter, because whenever I take any x which is within the distance of 80,000 from c, the corresponding f of x would be 1. And 1 minus f of c is also 1, will always be 0. So the distance is always 0. This is the happy situation where f of x is as close as it gets to f of c, namely it's always equal to f of c, right? And so it's no surprise that any positive delta worked. So the function is continuous at c, and c was arbitrary, so in fact the function is continuous at each and every real number, and so the function is continuous on R. Okay, so this was a very simple example where you could have chosen any delta you wanted. Now let's look at a little bit more complicated example where the function is not constant but instead the identity function. So the function from R to R just sends any real number x to the same real number. Okay, so the graph of the function is then like this. So the x is just sent to x itself. So the points on the graph are x comma x, which is this sort of diagonal line in R2. So again, we want to show continuity at any point C. We see that the graph of the function has sort of no jumps, so we expect the function to be continuous everywhere. So we want to show that. Again, we do some rough work. What do we want to check? Given any epsilon positive, we want to produce a positive delta, okay, which might depend on epsilon, such that whenever the distance of x to c is less than delta, I am guaranteed that the distance of f of x to f of c is less than epsilon. So this is what I want to achieve. I have been given an epsilon positive and I want to choose the delta positive such that whenever the distance of x to c is less than delta, I am guaranteed this. Now what is f of x in this case? F of x is simply x. And what's f of c in our case? F of c is equal to c. So this mod of f of x minus f of c is simply mod x minus c. And I want to choose a delta such that whenever mod x minus c is less than delta, I am guaranteed that this is less than epsilon. Well, I know that this is less than delta and I want this to be less than or equal to epsilon, so that then this is less than epsilon. So, if I choose any delta which is less than or equal to epsilon, it would work. For example, delta equal to epsilon by 2. And in fact, in this case, we can even take delta equal to epsilon. Okay, so any delta less than or equal to epsilon and positive would work. Okay, so this was the plan that we had, and now let's write it down and check that everything works. So let C be any real number, and I'm going to prove that f is continuous at C. So if epsilon positive is given to me, by my plan, I choose any delta which is less than or equal to epsilon and positive. For example, delta equal to epsilon works, delta equal to epsilon by 2, epsilon by 3, epsilon by 30,000, anything less than epsilon will work. Okay. So for simplicity, I choose delta equal to epsilon, that's a positive number. And then whenever my x satisfies that its distance to C is less than delta, okay, but the delta is then has been chosen to be equal to epsilon, we have that mod of f of x minus f of c. Well, f of x is just x, f of c is just c. So this is mod x minus c. What do I know about mod x minus c? Well, that's less than delta, which has been chosen to be equal to epsilon. So what have we checked? We have checked that given any epsilon positive, we have produced a delta, namely the same epsilon. You give me an epsilon, I choose my delta to be the same epsilon. Okay, so I produced a positive number delta such that whenever the distance of x to c is less than this delta that I have given you, now I have that the distance of f of x to f of c is less than epsilon. Okay, so we have exactly checked the statement in the definition of continuity at C, so the function is continuous at C. Well, what just happened? So here is C and here is f of c. You gave me an epsilon positive, so this f of c has been lifted up through a distance of epsilon and lifted down by a distance of epsilon, and then all of these points have their distance to f of c less than epsilon. And I wanted to guarantee that there is a delta positive, such that whenever I take my x's within a distance of delta to c, the graph of the function lies below this and above this. Okay, and I took this delta to be the same as epsilon. So if this height was epsilon, I take this distance also as epsilon. So when I have my x's over here, okay, then the corresponding f of x indeed lies below this and above this. But anything smaller would have also worked. So if this was height was epsilon, okay, you take it over here, and something smaller, for example, epsilon by 2 would land me over here, right? So it will be the midpoint of this one and midpoint here. So over here, when my x lies over here, then the corresponding f of x indeed would be, you will get this portion of the graph which lies below this and above this. That's over here. In these simple examples, you can just draw a picture and find the delta corresponding to the epsilon, and it's very clear in these simple cases. And also this choice of C in R, we didn't say anything about it. It could have been anything. and we can repeat this proof. So in fact the function is continuous at each and every c in R, and so the function is continuous on the whole of R. So far we have seen two very simple examples of continuous functions, the constant function and the identity function. Let's now see an example of a function which is not continuous. Okay, again something which has a jump. So here is the step function. I call it the step function because its graph looks like a step. Okay, and the function is defined like this: f of x is 1 if x is positive. So for all these positive things it's 1, but if x is equal to 0, then the value is 0, and if x is strictly less than 0, so all the negative numbers also have the corresponding f equal to 0. Okay, so the graph of the function for negative axis is 0, at 0 it is 0, so the value at f of 0 is 0, and then the moment it becomes positive it jumps up to this value of 1. So clearly there is a jump. We expect the function is not continuous at 0. Okay, so let's first prove this claim that the function is not continuous at the point 0. Okay, and let's prove this by contradiction. So we will suppose that the function is continuous at 0, then our definition tells us something, and we'll show that something terrible happens, we get a contradiction. Okay, so this is what f of 0 is. It is 0. Am I guaranteed that no matter what epsilon you give me, for example, I choose something smaller than this gap because then I already know there might be trouble. So I choose, for example, this height is 1, I choose something smaller than 1, say half. So if my epsilon is half, then I lift the value up through a distance of half and below through a distance of half. And the question is, can I choose a delta so that whenever I'm close to 0 within a distance of delta, I'm guaranteed that the graph lies in this strip that is below this line and above this line? And we visibly see that that's not the case, because no matter how small I choose this width delta to be, you will see that these are the points which get arbitrarily close to 0, yeah, on the domain side, but the corresponding f lies outside this strip. Okay, so I choose, according to my plan, epsilon something smaller than this jump height. Okay, the jump height is 1, so I choose anything smaller than 1. Let's choose epsilon equal to half. Okay, so since we are assuming that the function is continuous at 0 for this positive epsilon, I know that there exists a delta positive such that whenever x is within a distance of delta to 0, I have that the distance of f of x to f of 0 is less than half. But f of 0 is 0, right? So I just have that the mod of f of x is less than half. But obviously we know that for the points on the right of 0, okay, this is not happening. So let's take some x which satisfies this but is on the right of 0. So let's take x equal to delta by 2. Okay, so that's a positive number, it's on the right of 0. And then the distance of x to 0, x I have taken as delta by 2, so it's just delta by mod of delta by 2 minus 0, and delta is positive, so this is just delta by 2, and that's certainly less than delta. So my x, which is delta by 2, satisfies this. So then the corresponding f of x has to satisfy this. Its mod should be less than half. Mod of f of delta by 2 is 1, and mod of 1 is 1. So I get the contradiction that 1 is less than half, right? And so our original assumption that f is continuous at 0 cannot be true, and so the function is not continuous at 0. Okay, so is the function continuous on R? No, because there is a point where it fails to be continuous. Okay, of course there might be points where it is continuous. Okay, so for example, in fact the function is continuous at every c not equal to 0. So at all of these positive points the function is continuous. So if I take any c positive, the function is continuous there. If I take any c negative, the function is continuous there, but at 0 it is not continuous. Okay, so let's actually check that the function is continuous at any negative c. Okay, so I am going to show that our same step function is continuous at every c less than 0. Actually, in the vicinity of c, the function is just constant. So whenever I take x's which are close to c, the corresponding f of x is the same as f of c if I don't stray too far away. If I go positive, then suddenly the value changes drastically from the value at c, which is 0, right? Over here the value is 1, here the value is 0. So I should just make sure that I don't go too far away into the positive numbers. Well, I would not go far away, too far away, if for example I confine myself. So this is c, so the distance to 0 is actually minus c because c is negative. So as long as my delta is like c minus c by 2, which is a positive number, I will be confined to be in this region, and then the corresponding f of x will be also the same as the value at f of c. Okay, so that's the plan, and now let's carry it out. So suppose you give me an epsilon positive. Okay, I'm going to produce a delta. I take delta equal to minus c by 2. Okay, since c was negative, this minus c is going to be a positive number, and half of that is also positive number. So this delta is a legitimate positive number. You give me an epsilon, I say that, well, take this delta. Then whenever my x is in R and it satisfies that its distance to c is less than this delta, okay, then privately I know that since this delta was minus c by 2, when my x is within a distance of minus c by 2, I'm confined over here. But let's prove that. So, well, here is the proof. X minus c is of course less than or equal to its own absolute value, and this absolute value is less than delta, which is minus c by 2. So if I bring this c over to the other side, I get that x is less than c minus c by 2, which is equal to c by 2, which is negative. So indeed, as I suspected, when my distance is minus c by 2, I stay negative. And so the mod of f of x minus f of c, well, x is negative, so f of x will be 0, and f of c was also negative, so f of c is also 0. So this is just mod of 0 minus 0, which is 0, and that's certainly less than the positive epsilon. So given any epsilon positive, I have produced a delta, namely this positive number, because c is negative, so this is positive, such that whenever x satisfies that its distance to c is less than delta, I have that the distance of f of x to f of c is less than epsilon. So we have showed that f is continuous at this c. So for all the and c negative was arbitrary. So for all of these negative numbers, the function is continuous at each of these negative numbers. And likewise, you can show by yourself that f is continuous at each positive c also. And indeed, here the value will always be 1. So as long as, again, when c is positive, you can take the delta equal to c by 2, okay, which will be a positive number, and then you can check for yourself that the function is continuous at each of these positive points also. So to summarize, the function is not continuous on the whole of R. Why? Because if it was continuous on the whole of R, it would be continuous at each and every point, but we know that the function is not continuous at c equal to 0. So our function is not continuous at 0. It is continuous at every negative c, and it's continuous at every positive c. Okay. Alright, so far we have seen 3 examples. Now here is a 4th one. Okay. And suddenly now, for the epsilon, we will have to, given epsilon, to check continuity, we'll have to produce a very complicated delta to make it work. So the point of this exercise is not so much to show or give practice on how to produce all kinds of exotic deltas given a epsilon for some complicated function, but the point is we will soon learn some theorems which will make life easy, and we will not have to check the definition, but rather we can resort to these other tools to deduce continuity. Okay. Alright, so first let's do it by brute force using the definition, because then we will appreciate those other results a bit better. Okay, so that's the point, sort of. And also, of course, we'll get some experience with the definition as well. Okay, so the 4th example we are going to consider is this reciprocal function. Okay, so the function is defined on this interval. Now the interval is not the whole of R, but it's this open interval 0 infinity, so all the positive real numbers. And the function just takes an x, and f of x is then 1 by x, so it takes the reciprocal of this positive number. Now the graph of the function then looks like this. So here is the positive real line, okay, the half line, of positive real numbers, and then 1 by x will look like this. As you come closer to 0, the value is very, very large. For example, the reciprocal of 0.001 will be 1000, and as you go far away, the reciprocal of a million will be 0.0000 and then a 1. So it will be very, very small. So the graph looks like this. But the graph has no breaks, so we expect the function to be continuous at each of the points in its domain. The points in the domain are positive numbers, so let C be a positive number, and we suspect that the following claim is true, that the function is continuous at C. So what do we have to do to check this statement? From the definition, we have to check that given any epsilon positive, we want a positive delta such that whenever the distance of x to C is less than delta, and x is something in the domain, so it's positive, we want that f of x, which is 1 by x, its distance to f of C, which is 1 by C, so the mod of that, that's the distance, should be less than epsilon. And since I want to manipulate it, I wrote it in the opposite order, so epsilon first and then. So epsilon should be strictly bigger than mod of f of x minus f of C, which is mod of 1 by x minus 1 by C. Now, if you do some algebra here, you get xc in the denominator and c minus x in the numerator, which is the mod of the numerator divided by the mod of the denominator. Mod of the denominator splits into two parts, mod x times mod c, but c is positive, so you get just a c there without the mod. And the numerator, you see the mod of minus y is the same as mod y for any real y. So this is really the mod of the minus of this, which is mod x minus c. So given any epsilon positive, I want to make sure that this combination is less than epsilon. Just think of making this combination small. What are the things that we are allowed to make this quantity small? So we are allowed to choose a positive delta such that x is close to C. So I can make this small. Mod of the numerator mod x minus C I can make small. 1 by C, C is a fixed number. So this is just a scaling of that. So I can make this combination also small. What might be worrisome is whether 1 by mod x, does that stay small? Because if we manage to show that that does not become too large, say it's bounded by m whenever x is close to C, then we are in business, because then this whole combination is basically small due to this. This is not growing, as x gets close to C, and so this is just as well a sort of a constant. It can be bounded by a constant. Okay, so the question is, when x is close to C, does 1 by x stay bounded? Now, of course, I know that if I get very, very close to like 0, then I'm getting unbounded. But you see, if I choose my C is some positive number, so it has some, some distance to 0. And if I choose, say, something like half of the distance, and if I'm confined over here, okay, so the x just lies within a distance of C by 2 from C, so then I'll be over here, then the corresponding 1 by x's just lie in this portion, and it doesn't go beyond this value, whatever was the value over here. So then it stays below this, right? So it seems that somehow if I choose my delta sensibly, okay, so that I stay far away from 0, something like C by 2, okay, then I know that the corresponding 1 by x's don't go too far away, right? It will stay below this thing. Okay, so that's the plan. Okay, so let's carry out whether it works or not. Well, I know that if I am not too far away from C, 1 by mod x stays bounded, or in other words, this is, if I rearrange this is the same as saying that mod x is bounded from below. You take this over here and this thing. So that's what I wanted to achieve. So mod x, I know something about mod x minus C. Okay, so I would like to see this combination x minus C appearing. So I add and subtract this. So mod x is mod x minus C plus C. And by the reverse triangle inequality, this is bigger than or equal to the mod of mod x minus C minus mod C. Okay, which is furthermore bigger than or equal to minus of whatever is inside. So that will give mod C minus mod x minus C. Okay, so this is just an application of the reverse triangle inequality. And mod C is just C because C is positive. And what I'm saying is that as long as my distance to C is not too much, say it's less than C by 2, then you see that C minus this thing will be bigger than C minus C by 2, which is C by 2, and that's a positive number. So I've got mod x is bigger than something positive, and so 1 by mod x will be less than the reciprocal of this. In other words, 1 by mod x will be less than 2 by C whenever if I have chosen my distance to C less than C by 2. So what I want from my delta is that first of all it should be smaller than C by 2. Okay, that's one qualification, but then I also want this overall combination to be less than epsilon. And what do I know? Well, this overall combination is less than mod x minus C, and 1 by mod x I have just bounded. That is less than, okay, mod x is strictly bigger than C by 2. So 1 by mod x is less than 2 by C, right? So this 1 by mod x is less than 2 by C, and 1 by C, that I don't change at all. So I have that this combination is less than mod x minus C times 2 by C times 1 by C, and I want to make this whole combination smaller than epsilon. So what should mod x minus C be? Well, if it is less than, epsilon times the reciprocal of this. So if I choose the distance of x to C less than epsilon C square by 2, then you see the C square will cancel against this, the 2 will cancel, leaving a neat epsilon at the end. So we want the delta to be such that it's less than C by 2, so that this bound works, that mod of x is bigger than C by 2, so that 1 by mod x is less than 2 by C, and moreover we want the distance to the delta to be less than epsilon C square by 2, so that also the total combination of this thing is less than epsilon, so that then this is less than epsilon. Okay, so these are the two demands from the delta. It should be smaller than this red thing C by 2 and less than this blue thing. So you just take it to be the minimum of these two. Okay, so this is so far the rough work, the plan of the proof, and now we will actually prove it. Okay, so given the epsilon positive, I want to produce a positive delta such that whenever the distance of x to C is less than delta, I have that the distance of f of x to f of C is less than epsilon. How do I do that? Well, given this epsilon positive, I set my delta to be equal to the minimum of this number and this number. So it's the minimum of epsilon C square by 2 and C by 2. Okay. Now C by 2 is a positive number, yeah, because C was positive, and epsilon C square by 2 is also positive. So the minimum of these two is also positive number. Now, whenever I take any x in the domain, so x is a positive number, whenever x in the domain satisfies that its distance to C is less than delta, I know that since delta is the minimum of this, in particular mod x minus C is less than each of these numbers. So mod x minus C is less than C by 2 and also less than this one. Now, does this delta do the job? Does it make mod f of x minus f of C less than epsilon? Let's check that. So basically we have to retrace the steps now. So mod of f of x minus f of C is mod of f of x is 1 by x, f of C is 1 by C. Doing some algebra, we know that this is mod x minus C divided by mod x times C, mod C, but mod C is positive, so it's just C. And since mod x minus C is less than delta, okay, which is the minimum of these two, so then mod x minus C is also less than C by 2. We know that 1 by mod x thanks to this is less than 2 by C, yeah, because mod x minus C is less than C by 2. And moreover, since mod x minus C is less than delta, which is the minimum of these two, in particular mod x minus C is less than epsilon C square by 2, so this thing is less than epsilon C square by 2. So the C square cancels, the 2 cancels, leaving an epsilon. So given an epsilon positive, we have produced a positive delta such that whenever the distance of x to C is less than delta, you have that the distance of f of x to f of C is less than epsilon. So we have checked that statement in the definition of continuity, so the function is continuous at C. Okay, so we had to do a lot of hard work to just check that this function is continuous at any positive number. Okay, but we are soon going to learn a theorem which will make this a piece of cake. So very, very easy. By the way, since the C was arbitrary, the function is in fact continuous at each and every point in the domain, which is a set of all positive real numbers. Okay, so now we had to do a lot of hard work to prove this, but here is a theorem which will make it very easy. And this theorem is one of these nice properties which are possessed by continuous functions, which are not possessed by any old function. Okay, so general functions may not have this property, but continuous functions have this nice property. The theorem is summarized by saying, so this is a mnemonic you can remember, continuous functions preserve convergent sequences. Okay, so what does this mean? It means the following. So the setting is this. Suppose you have an interval and you have a point in this interval, and you have a function which lives on this interval and is real valued, and we are going to discuss the continuity of this function at this point C in its domain. This theorem says that the following two statements are equivalent. Saying that the function is continuous at C is exactly the same as saying that this statement holds. Okay, so what is this statement? This statement says that for every sequence xn which is contained in I, so each of these terms is an element in the domain of the function, and moreover the sequence is such that it is convergent with limit C. What is the C? The point at which we are discussing continuity. So whenever you have the situation that you have a sequence in the domain which is convergent with limit C, if I look at this new sequence f of xn, does that make sense? Well, xn is in the domain, so f of that makes sense. So this is a real number. Okay, and if I feed in x1, x2, x3 to the function, I get this new sequence, f of x1, f of x2, f of x3, f of x4, and so on. So that new sequence is also convergent, and moreover the limit of this new sequence is equal to f of c. Okay, so saying that the function is continuous is exactly the same as this statement, that no matter which sequence you take in the domain which is convergent with limit c, f of xn happens to be convergent with the limit of f of xn, f of c. F is continuous at c if and only if this happens. So to check continuity, now we have a new tool. If we manage to show that whenever a sequence is converging to c, f of that converges to f of c, then we can conclude that the function is continuous at c. Okay, and we have lots of tools to deduce convergence of a sequence, right? We have a whole toolbox to analyze that, so we can use that, and hence we can avoid this epsilon delta definition of continuity. Okay, so that is sort of a practical value of this theorem, but of course it has theoretical value as well, and we'll continue with this theoretical value next week also. But right now it has immense practical value, because to check continuity reduces to checking convergence of a sequence, right? Okay, so another thing, sort of this f of the c is actually the limit of xn. So here is a sort of nice way of succinctly remembering this, that f of the limit as n tends to infinity xn is the same as the limit as n tends to infinity f of xn. So whenever you have a sequence which converges and you look at this new sequence f of xn, then that's also convergent with what limit? The limit is f of c, and c is this thing. So it's as if, you know, this f and the limit, they are exchanging, and that exchange is allowed when you have a continuous function. Okay, so far we have not proved this theorem. The task is of course to prove this theorem, but let's actually revisit our reciprocal function and see how things become remarkably simple now. So let's revisit what the function was. The function was defined on the set of all positive reals, and it takes any x, and f of that x is then 1 by x, is defined by 1 by x. And we claimed that the function is continuous at every positive number. Okay, so now to check continuity at any c, it's enough to check this thing. What does this say? That whenever you have a sequence converging to c, so let xn be a sequence contained in this domain, so it's a sequence of positive numbers, and it converges with limit c. Okay, then the question is, does f of xn also converge with limit f of c? Okay, what is f of xn? Well, f of anything is the reciprocal of that. So f of xn, remember that xn's are positive, so the reciprocal is well defined, it's a non-zero number. So f of xn will be 1 by xn. Okay, and the question is, does 1 by xn converge to f of c? What's f of c? 1 by c. C is also positive, so 1 by c is defined. So the question is, given that xn converges with limit c, does 1 by xn converge to 1 by c? This should remind you of something that we have learnt a while ago, namely one of the statements in the algebra of limits. For this to happen, each of these numbers should be non-zero. Well, they are positive, so they are non-zero, and the limit should be non-zero. The limit is positive. So indeed, by the algebra of limits, since xn converges with limit c, 1 by xn is convergent indeed with limit 1 by the old limit, which is 1 by c. In other words, f of xn is convergent with limit f of c. So we have checked this statement that whenever you have a sequence which converges to c, f of xn, which happened to be 1 by xn in this case, converges to limit f of c, which happens to be 1 by c in this case, right? And so f is continuous at c. No epsilons, deltas, we just had to use the algebra of limits, and it was much more easier, right? Alright, so the function is continuous at c, this particular function, and since c was arbitrary, you get continuity at each of these positive real numbers. Alright, so it remains to prove this powerful theorem, okay? And to prove this theorem, we have to prove two implications, that 1 implies 2 and 2 implies 1. Let's start with 1 implies 2. So we know that the function is continuous at c, and we have to show that whenever a sequence xn converges to c, f of xn converges to f of c. Okay, so let's see how to do that. So we are proving the part 1 implies 2. So I know that the function is continuous at c, and given any sequence xn in this interval such that xn converges to c, what I want is f of xn converges with limit f of c. What does it mean to say that f of xn converges to f of c? Okay, which is what we want to prove. We want to prove that given any epsilon positive, there exists an index n such that beyond that index, the distance of the nth term to the claimed limit, which is f of c, is less than epsilon. So this is the statement we want to prove. What do I know? I know that the function is continuous at c. So for this positive epsilon, I know that there exists a corresponding delta such that whenever the distance of x to c is less than delta, I am guaranteed that the distance of f of x to f of c is less than epsilon. Okay, and what I want is the distance of f of xn to f of c is less than epsilon for all the indices beyond a certain n. Now, wouldn't it be great if my xn satisfies that beyond a certain index xn minus c is less than delta, because then this would be satisfied, and then automatically you would get for that xn mod of f of xn minus f of c is less than epsilon. So then we would be done because we will have this. So the question really is, does there exist an index capital N such that beyond that index the distance of xn to c is less than delta? And of course there is, because we know that the sequence xn is convergent with limit c. So given any distance, in particular delta positive, I know that there exists an index capital N such that beyond that index the distance of xn to c is less than delta. To show this sequence is convergent with limit f of c, what did we want to show? Given any positive epsilon, we wanted to produce an index such that beyond that index this happens. The way to do it is that given an epsilon positive, you use the continuity to produce a delta. You use this delta to produce the index n. Okay, and then we will be guaranteed that mod f of xn minus f of c is less than epsilon. Okay, so that's the plan. Okay, and let's carry out the plan in careful detail now. Okay, so here is how we proceed. So we are assuming that the function is continuous at c. We know we have been given any sequence xn which is in I such that xn converges with limit c, and we want to show that f of xn is convergent with limit f of c. So given any epsilon positive, I want to produce an index such that beyond that index the distance of f of xn to f of c is less than epsilon. The way we do this is like this. Given positive epsilon, I know thanks to the continuity of f at c that there exists a corresponding delta corresponding to this distance such that whenever x in I satisfies that its distance to c is less than delta, mod of f of x minus f of c is less than epsilon. Okay, so let's label this sentence as star. Okay, I have this delta positive and I know that the sequence xn converges to c. So for this distance delta positive, I know that there exists an index capital N such that beyond that index the distance of the nth term to the limit, which is c for this sequence xn, that is less than delta. So now for the little n which is bigger than capital N, okay, I know that mod of xn minus c is less than delta. So I have got an xn which is in I, all the xn's are in I, which satisfies this. You see, the mod of xn minus c is less than delta. So I know that this is true. Yeah. And so I know from this starred statement that then for whatever x you have which satisfies this, I am guaranteed that mod of f of x minus f of c is less than epsilon. So since I have that mod of xn minus c is less than delta, in other words xn satisfies this, I know that the corresponding f of xn satisfies this. So mod of f of xn minus f of c is less than epsilon, and this happens for every little n which is beyond this index, because all of those satisfy this inequality. Yeah, and so we have got what we wanted. So given any epsilon positive, I first find a delta thanks to the continuity such that blah 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 happens. For that delta, I know that there is an index such that the distance of xn to c is less than delta, and then I'm guaranteed that beyond that index, mod of f of xn minus f of c is less than epsilon. Okay, so given any epsilon positive, I produced a capital N such that beyond that index, this happens, and so f of xn is convergent with limit f of c. So given statement 1 that f is continuous at c, I have been able to prove that no matter which sequence you take which is convergent with limit c, f of that converges to f of c. So I have proved the second statement. Now we will show that the second statement implies 1. So we have already proved 1 implies 2. Now we go from 2 to 1. So the two statements are equivalent. Okay. So we have, it's still left to prove that 2 implies 1, which we now do. Okay. So to prove that 2 implies 1, instead I will show the contrapositive. So I'll show that if it is not the case that 1 holds, then it's not the case that 2 holds. Okay. So that's the same as showing that 2 implies 1. Okay, so I'll prove the contrapositive of 2 implies 1. I'll assume that not 1 holds. So I'll assume that the function is not continuous at c, and I'll show that the second statement does not hold. What does the second statement say? It says that no matter which sequence I take which converges to c, f of xn converges with limit f of c. To show that this second statement does not hold, it's enough to demonstrate one sequence xn which converges to c, but for which f of xn does not converge to f of c. Okay, so to show that the second statement does not hold, I just have to produce one such sequence. Okay, and that I will produce by using the fact that I'm starting with, namely that the function is not continuous at c. Okay, so I'm assuming that the first statement does not hold, so the function is not continuous at c. What does that mean? That means that it is not the case, and now I'll write what it means for the function to be continuous at c, that for every epsilon positive, there exists a corresponding positive delta, such that whenever x is in I in the interval, and its distance to c is less than delta, we have that the distance of f of x to f of c is less than epsilon. Okay. Right, what does that mean? It's not the case that for every epsilon blah blah happens, so there must exist a bad epsilon preventing this from happening, right? So there exists a positive epsilon such that this part of the sentence does not hold. What does that part say? That there exists a delta such that blah blah happens, so no matter which delta positive you take, the rest cannot happen. In other words, it is not the case for every x in I blah blah happens, so there must exist a bad x in I for which, despite the fact that the distance of x to c is less than delta, you have that this cannot happen. In other words, mod of f of x minus f of c is bigger than or equal to epsilon. Okay, so not this thing holding is exactly the same as saying that there exists a positive epsilon, such that no matter which delta positive you take, there exists a bad x, such that mod x minus c is less than delta, all right, but this does not hold. So mod of f of x minus f of c is bigger than or equal to epsilon. Okay, and I'll use this statement. To construct my sequence, which is such that although xn converges to c, f of xn does not converge to f of c. Okay, all right. So what is this telling me? There exists a special epsilon positive such that no matter which delta positive I take, there exists a x such that something happens. Now, for every delta positive, I'm guaranteed an x, okay, which satisfies this thing. So for example, if I take delta equal to 1 by n, where n is some natural number, so that's a positive number, I am guaranteed a corresponding x in I, which I label as xn. So given this delta, which is 1 by n, I have a corresponding xn, such that mod xn minus c is less than the delta that I chose, which is 1 by n, and mod of f of xn minus f of c is bigger than or equal to epsilon. Okay, so for every positive delta I was guaranteed a x. Okay, so in particular for delta equal to 1 by n, I am guaranteed a corresponding x, which I label as xn, such that mod xn minus c is less than 1 by n, but mod of f of xn minus f of c is bigger than or equal to epsilon. Okay, and let's call this star. So for example, if I take delta equal to 1, 1, okay, 1 by 1, then I have a x1 such that mod x1 minus c is less than 1, and mod of f of x1 minus fc is bigger than or equal to epsilon. Then I take delta equal to 1 by 2, that's also positive delta. There exists a corresponding x, which I'm calling x2. So there exists a x2 such that mod x2 minus c is less than a half, but mod f of x2 minus f of c is bigger than or equal to epsilon. Then I take epsilon equal to 1 by 3, there exists x3 such that mod x3 minus c is less than 1 by 3, but mod f of x3 minus f of c is bigger than or equal to epsilon, and so on. So I've got a whole sequence x1, x2, x3 and so on, all of which satisfy this and all of which satisfy this. I show that this first thing tells you that xn converges to c, and the second thing tells you that f of xn does not converge to f of c. Let's handle the first thing first, that xn converges to c, and that comes about because of this happening for every n. Indeed, this happening for every n, this thing is really equivalent to saying that xn minus c is less than 1 by n and bigger than minus 1 by n. And if I add c to all sides, that's the same as saying that xn is bigger than c minus 1 by n and less than c plus 1 by n. Right? So this thing is exactly the same as this one. You can convince yourself of that. Long ago we proved a little lemma where we proved this. Now this is happening for every n, but you see that this sequence, by the algebra of limits, 1 by n converges to 0 and c converges to c. So by the algebra of limits, the sequence whose nth term is c plus 1 by n, that converges to c. Similarly, the sequence whose nth term is c minus 1 by n, as n tends to infinity, converges to c. So this converges to c, this converges to c, and xn is in between the two. So by the sandwich theorem, that also converges to c. So I have shown that xn converges to c. Okay. So what was the task to show? We wanted to show that this second statement does not hold. Okay. So I have produced a sequence xn such that xn converges to c, but now I'll show that f of xn does not converge to f of c. Okay, that will show that the second statement does not hold. Okay, so I want to show that f of xn does not converge to c, f of c. And what do I know about f of xn? I know that this holds. For every n, f of xn minus f of c is bigger than or equal to epsilon. And of course that shows that f of xn does not converge to f of c. Why? Because intuitively, this would mean that the distance of f of xn to f of c can be made as small as I please if I go far enough in the sequence. Okay, but I know that the distance of f of x to f of c always stays above this epsilon. So if I choose some distance smaller than epsilon, say epsilon by 2, then I can never get closer than epsilon by 2, because the distance is always bigger than epsilon, so it can never become smaller than epsilon by 2. Okay, so that's going to be the source of our contradiction. So suppose that f of xn does converge to f of c, and we'll arrive at a contradiction. Okay, so suppose that f of xn, suppose it does, what I mean is, suppose f of xn converges to f of c, then no matter what distance you give me, there's a large enough index such that beyond that index the distance of the nth term is closer to f of c within that distance. Let's take the distance to be epsilon by 2, so that we get a contradiction with this one. So epsilon by 2 is certainly a positive number, and since we have assumed that this sequence is convergent with limit f of c, there should exist some index such that beyond that index the distance of the nth term to f of c is smaller than epsilon by 2. Now, on the one hand, we know that mod f of x n minus f of c is less than epsilon by 2 for all these little n's beyond this capital N. But on the other hand, we know that for all n's, this is true. So this is also bigger than or equal to epsilon. So we get that epsilon is strictly less than epsilon by 2. Epsilon is positive, so you can cancel that, or rearranging this, you get that 2 is strictly less than 1, which is of course absurd. So we have arrived at a contradiction, and this contradiction shows that our original assumption that this sequence is convergent to f of c is not true. So f of xn does not converge to f of c. So we started with not the first statement holding. So we know that f is not continuous at c, and we showed the second statement is not holding, because for the second statement to hold, for every sequence which converges to c, f of xn should converge to f of c. But I have now constructed a sequence xn. Over here we have constructed a sequence xn in this manner, such that although xn converges to c, f of xn does not converge to f of c. So we have showed that the second statement does not hold. In other words, we have proved the contrapositive of 2 implies 1. We have showed that if it is not the case that 1 holds, it's not the case that 2 holds. Okay, so this completes the proof of this theorem, and next time we will see some more theoretical applications of this one. And this is a very useful theorem because it allows you to check continuity via sequences, via convergence of sequences. Okay, so we'll stop here.